that. Okay, so let me pull up the periodic table that I sent to you, already marked. And I'd like to use the periodic table to figure out the electron configuration. As I stated before, you're more than welcome, obviously, if that works for you, to use that table in that chapter on the sequence and memorize that sequence. And that's okay. You can do that. That works for you. I kind of like to use the periodic table because I refer to this periodic table immensely because it is loaded with information. Okay. So, all right. So let's grab one. Let's arbitrarily grab a element, and what we're going to do is we're going to do the electron configuration for, let's see, chlorine. Okay. Someone has a question. Oh. Okay. Yes. That's true. The periodic table you'll find later on when we get into this the next chapter, that just by looking at where the element is on the periodic table, you're going to just get a lot of information very quickly. Okay. So I just read that element number 19, they're working on it. So they're trying to make element 119. So maybe they'll succeed. Who knows? So let's take chlorine. Okay. Notice I said the word chlorine. Chlorine is the element. So we are talking about the element and not chloride, which is the ion which gain an electron. Okay. All right. So I'm given the question, give me the electron configuration for chlorine. So I take my periodic table and I find it. I go look for it. There it is. It's sitting there, number 17, chlorine. Okay. So the first thing I notice is I identify is what period it's in. Okay. Because remember, the periods, which are the horizontal rows, represent the energy levels where these electrons exist. Okay. And so I can see that it's in the third period. Okay. So that's one thing I noticed. Second thing is I also identify it that it is part of the P block, the P elements. Okay. It's in group 7. Okay. So that tells me, will give me a hint as far as the P orbitals. Now, there's only 4 orbitals. These are the energy levels or the shells, and within these energy levels, there are subshells, but we use the term orbitals. Now, in the first shell, there's only one orbit, and that's the S. Okay, and the second shell, there are only 2 orbits, and that is the S and the P. And in the third, we continue to have the S. And we also have the P, but the D's come into play. So in the third level, we got the S, the P, and the D. Also remember that the order in which I fill these orbits with electrons are S first, followed by the P, followed by the D, and then if I ever get to the S, finally by the S. Okay? So I have 17 electrons to work with. Okay, 17 electrons, atomic number 17. I got 17 protons, 17 electrons. Being that it is in the third period, tells me that the energy levels in 1 are full and the energy levels in 2 are full. Okay, because we start with the bottom first energy level, fill that up with electrons, which can only handle a maximum of 2. Okay. We go into the second energy level, second period, there are only 2 orbits. The S can handle 2, the P can handle 6. So I can only put 8 total in that energy level, in the second energy level. The D has 3 orbits, the S, the P, and the D. So the maximum number of electrons that I can put in the third period are 2 from the S, 6 from the P, and 10 from the D. So how many is that? We got 18. So in the maximum number of electrons I can put in the third energy level are 18 total. Okay, so I start sequentially. Since it's in the third energy level, I can very quickly write that first energy level, which is 1s and then superscript 2, because it's full. That takes care of 2 of the electrons of the 17 to work with. Now I gotta sequentially add the other 15. Since the first energy level is full, I need to go to the second energy level, which begins with 2s, okay? And we can only put a maximum of two electrons in the s. So I very quickly can write 2s superscript 2, okay? So that takes care of a total of 4 of the 17. Remember, the superscript is the number of electrons that I have. Well, as I'm going across, now, if you look, I'm at 4 electrons. So who else has 4 electrons? Well, look at that, element number 4, beryllium. So I got to go across now to element number 5, and guess what? That's where the P's start, because those are called the P block. And I'm still in the second energy level, so I start with my 2P superscript 6. Why 6? Because I went all the way across where boron is the number 5 to neon, where is number 10. So at this point, count my electrons under my electronic configuration. I got 6 in the 2p, 2 in the 2s, and 2 in the 1s. That's a total of 10 electrons, okay, of the 17 that I need to work with. So since I'm at neon now, I got to go around the horn, so to speak. It's an old baseball term, around the horn. So where's the next energy level? Obviously, it's in the third, correct? So I'm back where sodium is, number 11. So I'm going across, all the way across to chlorine. And so the 2s is full. So I can put 2 there. That takes care of 12 electrons. I got 5 to go, okay? And now as I'm done with sodium magnesium area, I'm moving across the periodic table to aluminum. I also notice that chlorine is in the 5th column of the P block. So that tells you I have 5 electrons, okay? And so it's 2P and then superscript 5. Count your electrons, my superscripts. I should have, what did I,
P5?
okay. Yeah, that's a 3, thank you. Let me wake up here. All right, thank you. And that should be 3p5, okay? And saying count the superscripts, I should have 17 superscript, a total for 17 electrons. So there is the electron configuration. We know that chlorine is in group 7, which tells you you have 7 valence electrons to work with, which happen to be in the third energy level. Remember, valence electrons are the outermost electrons. And of those 7, 2 of them exist in the s orbit, and 5 of them exist in the p orbit for the valence electrons. Now, if I needed to go to the next element, which would be argon, I simply have to just change that 5 to, guess what, a 6. And now I'm at exactly 18 electrons, and that is the electron configuration for argon. And sequentially, if I go into number 19, back to potassium, I will go around the horn, okay? Potassium's in the 4th period. And if I needed to write the electron configuration for that, for potassium, it's in the 4th period, 4th energy level. It's in that S1, it's a S block, and it's got 1 valence electron. And I write it like so. So that would be potassium at this point. So that would be the electron configuration for potassium. Now, there is a shorthand way to write this, okay? And if you were asked, unless the question says do not use the shorthand way and it just simply says do the electron configuration for potassium, you can look at potassium, number 19, look at the search for the oh, let me make that okay, tap it okay. Search for the neon, the noble gas behind it. Well, who's the noble gas behind number 19? That would be argon, right? So I can very quickly use the bracket key and put its symbol and bracket and write 4s1, okay? So that would be the electron configuration for potassium using the shorthand method, okay? And I would accept that completely, okay? Unless the question says no shorthand, okay? And the thing to remember is make sure you put the bracket around the noble gas. Okay.
So when you use shorthand, it's always going to be a noble gas, like it's going to be the closest noble gas.
Exactly. Let's do number 37, rubidium. Okay. RB. Okay, so if I needed to do the electron configuration for that using the shorthand method, RB 37, the noble gas behind it is number 36, right? Which is krypton. Don't forget the brackets. That's the correct configuration. RB is in the fifth, excuse me, I got 10 fingers, in the fifth period, correct? So that's 5, and it's in the first column, 5s superscript 1. So that will be the shorthand configuration for RB. And if I needed to do strontium, number 38, guess what? I just put a 2 there for SR. Okay. And that is, again, the shorthand configuration. If you go back up to potassium, if you look at the electron configuration for argon, it is 1s2, 2s2, 2p6, okay? 3s2, 3p6. All of that can be put in the bracket with the symbol of argon and place it, and then you do the rest for potassium, 4s1. And again, that note of when potassium, you know that it's in group 1, it has 1 valence electron, okay? And so it's a metal, it's going to lose that electron, become an ion, and when that happens, guess what its electron configuration is? Put a plus sign, right? Because it's a charged species, and I can very quickly just say argon, okay? Oh, wrong bracket. Okay, for the potassium ion. Okay, for the potassium ion. Okay, so that's an example of just using the periodic table to determine the electron configuration. Okay, just follow a sequence.
Will we have any questions on further tests that require us to put it in shorthand?
There will be questions that ask you to write the electron configuration. They may even state don't use a shorthand, but if it doesn't say the words do not use shorthand, you're more than welcome to use the shorthand. Does that answer your question?
I'm still a little confused by it, but I'll figure it out.
Okay. Well, we can do more examples if you come to the office hour. We can do some more examples. We pick them out, whatever element you want, we can work through it. Okay?
Okay. All right. Thank you.
All right. All right. Well, let's, any other questions on electron configuration? Okay. We use electron configuration to help us understand what is happening chemically why is it that there's a bond between sodium and chloride later on as we start making compounds? And again, when these elements start to gain or lose electrons, you can see that depending what it is, if it's a metal, it will always lose an electron. If it's a non-metal, it will always gain electrons. And when that happens, it fulfills the octet rule. And that is the driving force when these compounds are being made, by losing or gaining electrons depending on the elements. All right, so that brings us to chapter 6. Chapter 6, fairly short chapter. It deals with the periodic table. Okay, kind of a little background about the periodic table. And we call it periodic table because there's a lot of periodicity. There's a lot of things going on as far as chemically that occur because of the position of the element on the periodic table. We talked about valence electrons. Everybody in group 1 has one valence electron. And because of that, they have all the elements on that group 1 would have very similar type of reactivity, simply because of that one valence electron. Okay, so the periodic table goes way back, 1869. Dmitry Mendeleev. Mendeleev was a Russian scientist that arranged the tables in order of increasing mass. He also arranged it on how they reacted, which is pretty amazing for the time period because they really didn't have any, modern equipment, so to speak, as we have now. His order of his table was strictly based on observation, observing the reactions and similarities, and he came up with his periodic table way back when. He actually predicted the existence of, at that time, 10 other elements, of which 8 were shown to be the case. But he's attributed to creating the first periodic table. Well, further down the road, another scientist by the Moseley, I believe you pronounce, what he did, he created his periodic table based on increasing atomic number. Mendeleev didn't have that information, and if he would have, he probably would have a very similar periodic table. And so Moseley is attributed to having or creating what was called the periodic law, meaning that elements in the same column have very similar properties. And now you know why. Because elements in the same column have the same number of valence electrons, okay? And therefore would have similar properties and similar reactivity, okay? Now, notice in the periodic table that we utilize, the group down at the bottom, the 2 rows are really belong inside. So in the far left, number 58 really belongs obviously after number 57, okay? But they take them out to kind of crunch the periodic table in to be able to see a little bit better. And what this is the period with the long periodic table with that special group inside, okay? Now, what they're also trying to do is notice the numbers on top, 1 through 18. They're trying to eliminate, they want to eliminate the Roman numerals and put in the sequential numbers 1 through 18. A lot of pros and cons. Obviously, I prefer the Roman numerals because that tells me right away how many valence electrons are involved. But that's still going around. In the meantime, there's been 50 plus different periodic tables that have gone around. Here's another example of an alternative periodic table. It has some pros and cons about it. So this is the spiral periodic table. And even here's another one. This one's not bad because it predicts up in the white area called superactinides. It predicts where the new elements would exist. But again, this also has some pros and cons with it. So anyway, the argument continues. Eventually, they're going to settle on something, but we will continue using the periodic table as has been developed by Moseley. Now, I already talked about the S block, the D block, the P block. That's because of Niels Bohr's work, that he introduced the idea that electrons exist in specific energy levels. And from that idea progressed this whole new area in what we call quantum mechanics, which is beyond the scope of Chem 130. But from that, a lot of mathematical equations came about and ended up with the orbits, the S, the P, the D, and the F block. Okay. Now, I already mentioned this, the horizontal rows, we call them the periods, / energy levels / gaps. Okay. The verticals are called groups. Sometimes they're called families, simply because they have similar reactivities. Okay, because they have similar properties. Okay. Now, all of the A, the ones in Roman numeral A, those are main group elements. The B's, which are the D block, are called the transition metals. Okay, they have their own little special name. So the main group elements are groups 1A through 8A, and then the transmission metals are the D block and the F block. Okay, so here's again the period, again with respect to the energy level. Okay, so you can already probably make a prediction just based on what we talked about. I mean, if I were to ask the question, okay, if I had to make a conclusion, who do you think will be bigger in size diameter-wise, lithium or potassium? Can I make a prediction based on this position on the periodic table? Anybody want to take
Potassium.
Exactly, because potassium is in the 4th energy level, meaning that it's bigger. Okay, so you already picked up on the very first trend with respect to elements. That is, as you go down the periodic table, the elements get bigger. Okay. Let me erase that. Now, again, the groups are labeled by their Roman numeral. Okay, so everything in blue is in the same group. Now, remember, hydrogen is in group 1. Even though it is placed in that group, it's not a metal. Remember that, okay? It is a non-metal. Now, the reason it's put in that group because hydrogen is very special, kind of special with respect to electrons. All right, we know that hydrogen has 1 electron, correct? And so that being the case, its electron configuration is simply 1s1, okay? And we all also know that hydrogen has 1 valence electron because of that. And this is, let me write this for hydrogen, electron configuration. And 1 lowly electron, it can very easily lose that electron. And when that happens, it now has a positive charge, okay? And that guy is what is roaming around in your stomach right now. That has a special name. We call that a proton. That is what's roaming around. That is what all acids have. A hydrogen that lost the electron to create an H+ ion, which we call a proton. Now, the other aspect about hydrogen, we should actually also put it under group 7, because it has the capability not only of losing that 1 electron, but it can pick up an electron because there's room for it in the s orbit. So you see how the electron configuration can hopefully give you a picture of why certain things occur. So 1s2, when it picks up an electron, guess what? now becomes 1s2 because it picked up an electron, and now hydrogen has a negative charge. Okay, just like the fluorine, chlorine, and the bromine. We call that guy, it has his own special name. We call him a hydride. So hydrogen is very special, but the point here is not only can it gain and lose an electron, we put it in group 1 simply because it has a one valence electron. But remember, it is not a metal. Okay. Now, some of these groups have their own special name. Like, for example, everybody in group 1A is called the alkali metals, except hydrogen. It's like I just explained, hydrogen is not a metal. The group 2A is the alkaline earth metals. They have their own little special name. Now, group 7 on the other side of the periodic table, where fluorine, chlorine, and bromine now, they have their own name. They're called halogens. You might be familiar with them because some of you are probably driving in a vehicle with halogen lamps, okay? And then the last group, as you well know, those have their own special name called noble gases. Okay. Now, the group B, those D blocks, okay, they're called the transition metals. We cannot predict very well their loss of electrons. They're all metals, they're going to lose electrons. You know, it's difficult to predict because they're capable of losing a multiple different number of electrons. For example, copper, which is Cu, that's elemental copper, pure copper, can lose 1 electron and have a +1 charge. But it can also lose 2 electrons and have a +2 charge. Okay? So copper is number 29. Iron, which is number 26, can have a +2 or a +3 charge. So transition metals are difficult to predict with respect to their charge. We will be able to determine what charge they are when they're put together with a compound, and I will address that when we get to that. Excuse me. Now, the intertransition metals that roll down at the bottom, they have their own special name. The top row, starting with 58, are called the lanthanide series. They also have a alternative name called the rare earth metals. A lot of them are used in electronics and so forth, and expensive metals. In the second row, they're called the actinide series. All of them are radioactive. In fact, starting with number 93 and above, those are all man-made elements. They put them in a particle accelerator where you're blasting particles with each other at very high speeds, very high speeds. Okay, now, that being said, if you're asked, can you name an alkali metal in the third period? Okay, and so we look at the periodic table, look for the third period. We know that the alkali, based on what I just told you, is group 1, so that has to be sodium. Okay. Second question says, name a halogen in the second period. Well, we find the second period, shoot across to the halogens, which is group 7, and that can only be fluorine. Okay. Notice again, I said fluorine. And then a noble gas in the fourth period. So we go to the fourth period, noble gas is in group 8. So the only noble gas that has to be is krypton.
Dr. Fred,
Yes.
could you quickly go over what a halogen is one more time? I'm sorry.
Yeah, okay, no problem. Halogens are the ones in, let me mark it. Everybody in that group, group 7, has a general name of a halogen, okay? And so when they ask the question, a noble gas in the 4 period, we count down 1, 2, 3, 4. So that, excuse me, if they ask you for a halogen in the 4 period, then that would be bromine. Okay? So halogens, the name halogen is just, the halogen is just a name, the general name for everybody in group 7. Alkali metals, group 1, alkaline alkali earth metals, group 1. Let me go back to it. Let me clear my screen. Alkali metals in group 1, alkaline earth metals group 2, the halogens in group 7, and the noble gases are in group 8. Those are the general names for those elements in those particular groups. And then, of course, the F block, they have their own little name series. One is the lanthanide series, and then the second one is the actinide series. So remember when we talked about metals, nonmetals, and metalloids. Again, I'm bringing this up here to refresh your memory. The light green from my screen are the metalloids. Okay, the reddish light pink color are the nonmetals. Okay, and then the light blue color are all metals. Okay. Now, when we talk about atomic size, all we're basically saying, what is the radius? What is the distance from the nucleus to the outermost electron? Okay. And what you already gathered from my earlier question is as you go down the periodic table, excuse me, my phone's ringing, sorry, I thought I shut it off. Okay. As we increase down the column, it's not working. As we go down the group or down the column, the radius increases. That's the reason, because we go into a different shell, different energy level. Okay. And so we get bigger energy levels, bigger radius. Now, the troubling part is this part, that is we go across the periodic table, whichever way you want to go, either left to right or right to left. Okay, if we go from right to left, the radius gets bigger. I prefer to go from left to right, right? Because that's how we read. But as we go from left to right, okay, the radius of the atom gets smaller. Okay, let me pull up one of these. Okay, so we know, change the color here. So we know that we just talked about if we compare lithium with, say, potassium is going to be bigger in radius simply because potassium is in the 4th energy level. Okay, but if we compare lithium with fluorine, the order reverses, meaning that from left to right, the radius gets smaller. Okay. We're still in the same period. We haven't gone down in the energy levels. We're all in the same 2nd energy level. So the question is, why is that? Well, think about this for a second. Lithium has 3 protons and 3 electrons. Fluorine has 9 protons and 9 electrons. Okay. Now, the protons, remember, are positive. The electrons are negative. So there is a force of attraction between them. Fortunately, they don't come in and crash with each other. The neutrons have a big factor in keeping them separate, okay? So, but there's still, nevertheless, there is a force of attraction to it. So if I were to have more positive charge and more negative charge, that force increases. So with fluorine having a lot more protons and a lot more electrons, it tends to pull the electrons into itself much greater than, say, lithium, okay? Hence, the radius of the fluorine is much smaller when compared to any of the other elements behind it within the same period, okay? Within the same period. And so even neon, which is the next one over to fluorine, would be smaller in radius than fluorine, okay? Carbon and nitrogen, which one do you predict to be smaller, carbon or nitrogen? Anybody want to take a guess at that?
Nitrogen.
Exactly. If I'm comparing these two, because nitrogen has one more proton, one more electron. Okay, so that force is a little bit greater and hence pulls the electrons into itself at a greater force than carbon. So nitrogen would be smaller in diameter. That's correct. Let's go back to this. And that is the explanation given here. And so if you go from right to left or left to right, it is the same reasoning. It has to do with the number of protons and the number of electrons having more force as you increase the protons, electrons, and hence pulls the electrons further onto into the nucleus. Okay, and so kind of to help you out, you can use a snowman here to help you out, where the circles represent the diameters of the elements. So as you see, as you go down the periodic table, where's it at? As we go down the periodic table, the diameter increases. And as we go from left to right, diameter increases. Or if you want to call it right to left, the diameter, did I say decreases? Left to right, decrease, right to left, increase, okay? And the counter for the other one. Whatever works best for you to remember. But the snowman's a good little a guide to help you out with respect to the radius. Okay. Now this picture, now obviously there's always rules, exceptions to the rules, but the general trend, as you see, as you go down the periodic table, these represent the radius of the atoms. As you go down the periodic table, they get a little bigger. And as you go from left to right, the radius gets a little smaller. So that gives you a general idea that the general trend, that is what you're seeing. Okay. So you might be asked the question, okay, I have oxygen, selenium, and beryllium. Which is larger? So I go find them in the periodic table. Okay, I got them marked with that little circle there. And thing I noticed, they're in the same group. They are in group 6, okay? And so that being the case, obviously terbium is bigger because it's further down on the periodic table, okay? Next question says magnesium, silicon, and sulfur. Which one is bigger? Well, I got to find them in the periodic table. You can see them here at the bottom. You got magnesium in group 2 way out to the left, and then all the way across to sulfur, okay? And so which one larger would be magnesium, okay? Because silicon and sulfur have more protons, more electrons, and they tend to pull the metals closer onto themselves. And so we do have videos talking about the atomic size, so you'll have this one here, so do watch and give you more information. Because we're going to talk about what's called the ionization energy. If you take a neutral atom, okay, that what ionization energy is simply the amount of energy necessary just to remove an electron from a neutral atom. So we take an element, we hit it with some energy, and we want to kick off an electron, okay? And we measure the amount of energy it takes to pull it off. Okay? And what you see up here is a general reaction where you got sodium undergoing the process to give you the sodium ion plus the electron. That is the ionization energy. Next few slides, we're going to be talking about the electronegativity. Those are two different things, okay? Two different things. Here, the ionization energy, simply put, is the amount of energy to remove an electron from a neutral element or atom, okay? So we find that the ionization energy increases as we go up a group. So it's easier to remove electrons from a larger atom. And if you think about it, it makes kind of sense. If we look at the periodic table, let me pull up the periodic table again. That's why I said I referred to it quite a bit. If we look at the periodic table and let's compare lithium again. Sorry, let's clear that again. Let's compare lithium with one valence electron with cesium with one valence electron, okay? Now, they both share the property of one valence electron. However, cesium is in the 6th energy level compared to lithium, where that valence electron exists in the 2nd energy level. So obviously, that electron for cesium is further away than that electron, that valence electron for lithium. And so the interaction of the valence electron of cesium with the nucleus is much less than the interaction of that valence electron for lithium and its nucleus, okay? And so by rights, if I hit it with energy to remove that electron, it would not take too much energy to take one off of cesium because it's further away from the nucleus, less interaction than lithium. Let's go back to remove because it is further away. Now, going from the left to right, the ionization increases, okay? For a couple of reasons. A good way to remember that is when we go from left to right in the periodic table, we start moving away from metals and start moving into nonmetals. And nonmetals want to gain electrons. Okay, that's point number one. The second point is, as we saw with respect to the radius of the atom as we went from left to right, we increase the number of protons, we increase the number of electrons as we go across the periodic table left to right. So those electrons are held down tightly, more tightly than the electrons on the left side. So it's going to take more energy to remove an electron from those elements that, back to the periodic table, it's going to take more energy to remove those electrons that are held on tightly as we go across the periodic table, okay? Simply because there's more protons, more electrons, and there's more force to hold them in. So that's the second point. And the first point, like I said, as we go from left to right, we start moving into the nonmetals that have a tendency to gain electrons much more so than metals, okay? As we go down the periodic table, those electrons are, the outermost electrons are further away and there's less interaction with the nucleus and therefore much easier to be removed, okay? As the question was about the F group with respect to ionization energy, it does, okay? But you're gonna find with the next slide that when we get into much bigger elements, we see the energy difference to start to be less. And I'll demonstrate that here in the next slide. Let me go back. This is a plot of that energy required for the ionization energy as you go across the periodic table. If we look at, let me make sure I change the color so we're not at the same color as the line. But as we go across the periodic table, where we start here with hydrogen and go across to helium, going across the periodic table, notice the ionization energy goes up as we go from hydrogen to helium, okay? The trend shows that. So from helium, we wrap around to go to lithium. So this is going across, starting here to neon, that's the second period. Notice the energy required increases as we go across the periodic table. And that's the second period. That brings us around to sodium, and we go across to argon on the periodic table, and the same general trend, but notice it gets smaller and smaller because the elements get bigger and bigger. And if we continue across each period, you notice that arrow is tending to kind of flatten out a little bit, but still the general trend is as you go across the periodic table, it requires more energy to remove an electron as you go from left to right. Eventually, as you get to bigger and bigger elements, they're all just bigger elements, and the interaction with the valence outermost shell is much less, just simply because of the size. And so that arrow tends to flatten out as we go to bigger elements, okay? Okay. Amanda, you had a question. Were you talking about the ionization energy or the radius?
I was talking about the radius, like for group F, like I think it was a table that you showed us on Tuesday of the atom sizes.
Mm-hmm.
And like if you look at group F, it's,
yes.
Yeah, that right there.
Right.
It seems like the size isn't decreasing from left to right. It just seems like the sizes are kind of bouncing back and forth between bigger and smaller.
Yeah, because they're so big. When you get down to that group, the F block, those elements are so big. And so the atomic size, that trend doesn't really fit too much for it. But if you're asked the question for Chem 130, yes, the trend would be yes.
So they don't increase or decrease in size, because that was the question that I asked.
The general trend would be decreasing as you go from left to right.
Okay, so the circles are just not correct.
Yeah, no, the circles are correct. Okay, all right, let me restate that. You can see from the other elements of the trend get smaller. The numbers underneath represent which element isotope we're working with, okay? So you can see from the main group elements, the trend decreases as you go from left to right, correct? As you go from, as you go from sodium all the way across to argon, you can see the diameter is much smaller for argon than it is for sodium, right?
Yes.
Okay, and the same would be true for potassium. The next group up as I go across to krypton. And if I go from rubidium all the way across to xenon, again, the diameter tends to get smaller when you get down all the way across, correct?
Mm-hmm.
Yeah, so in the F, you are correct. In the S, the trend, they seem to be just about the same. And that's a true statement, okay? But you won't be asked any questions about the F block. Let me put it that way. So when it comes to the rest of the elements, that's a general trend. They get smaller as you go from left to right.
Okay.
And if you were asked something about the Fs, you'll say, no, they're basically all the same.
Okay.
Okay?
Thank you.
Sure, no problem. All right. Where were we? Right here. Okay, so you may be asked the question, which has a larger ionization energy and why? And so you're asked here, chlorine, aluminum, magnesium. Okay, now you can look them up on the periodic table and find their position and go that route. But you can recognize that too, which of these three is a nonmetal?
The chlorine.
The
Or
chlorine. That is correct. Aluminum is a metal, magnesium is a metal, the chlorine is a nonmetal. And all nonmetals want to gain electrons, so they're not going to give up their electrons very readily. It's going to take energy. They will give them up, but it's going to take more energy. And so just by virtue of the fact that we're comparing one nonmetal and two nonmetals, the answer is by default the chlorine. Okay? Then, but if you don't remember that, then you find it in the periodic table, and you can see across the periodic table, the trend is the ionization energy increases. Again, because it picks up more electrons, more protons, and the electrons are held down to each other more tight than aluminum and magnesium.
so
Okay?
you're saying that any of the elements that are closer to the right side, if they're nonmetals, they're going to have a higher level of ionization energy than, say, the left side, because those are metal.
You're correct. Any nonmetal, when you're comparing nonmetal and metals, the nonmetals are always going to beat out the metals. Okay? Does that make sense? Because the nonmetals want to gain electrons, and you'll find that the nonmetals happen to have more protons and more electrons, and therefore hold on to the electrons much tighter, especially when it comes to the metals themselves. Okay? Does that answer your question?
Yes, it does. Thank you.
Okay, sure. Now, if I'm comparing just all nonmetals, then I got to find their position in the periodic table. Okay? So here we got I got all metals here, so I can't use the nonmetal thing, so I have to go in there and find out where they're at in the periodic table. And I got lithium, rubidium, and potassium who happen to be all in group 1A. And simply, which one would be the higher ionization energy? Would be lithium, because lithium is the smaller one of the three. Rubidium, RB, is down period, what is that, 5/5 energy level, okay? So its electron is like way out there compared to lithium. So its electron will be removed very much more readily than lithium. Okay, so we do have ionization energy videos, so make sure you get to read them. Now, this concept here is very important, because this tells us we have to grasp this concept, because when we start talking about chemical bonds, once we recognize electronegativity in a bond, that tells us a lot more information with respect to what we call polarity, okay? But we have to recognize this concept here. Now, as compared to ionization energy, what we dealt with was a single atom. In this case, we are talking about the atom that tends to pull electrons toward itself in a bonded scenario. Okay, so we're looking at a compound of some sort. And the bonding, when we get into it, is not an equal bonding. Sometimes it is an unequal bonding. And that unequal bonding will give us, tell us about the property. For example, oil and water. We all know that oil and water do not mix, okay? In the oil scenario, the bonding there is more of an equal sharing bonding, and that result is that oil has what we call a nonpolar property. Water is what we call a polar property because there's unequal sharing in the molecule of H2O. Okay. I use makeup as an example, perfect example. You know, I was once told that there's hurricane-proof makeup out there. You can survive a hurricane, but your makeup will be standing still there. Then there's makeup, obviously, like Halloween makeup, cheap makeup that washes off in water. Okay. Well, that hurricane-proof makeup, what do you need to get it off? Okay, so maybe, what is normally used right now to remove most makeup?
Oils?
Oils, exactly. You couldn't use soap and water because it's not going to take it off. So you use an oil cleanser to remove that makeup. So that infers that your makeup is very non-polar. And so those bonds in that makeup are shared very much. Whereas a makeup you use soap and water to remove, that infers it is a very polar makeup. And there, that means that the bonds there are not being shared, okay? And it's all being related to this electronegativity. Now, to determine which is more electronegative, you use fluorine as your benchmark because fluorine is the most electronegative element on the periodic table. And so the trend for electronegativity is from left to right, it increases. And from the bottom up, it increases, and they all point to fluorine in the corner there, okay? So, excuse me. Now, noble gases, they don't have any electronegativity, okay? Because one, they have electrons are full, the octet, they're happy, no more reactivity involved with them. Okay, so they're not going to be pulling anything. But we're going to talk a lot more about that in the next chapter with electronegativity. So the thing to remember is electronegativity is a measure of the affinity for an element in a bonded situation to pull electrons onto itself. Okay? So that being said, guess what? We're done. All right. Now, I'm gonna leave it as such at chapter 6. We'll start chapter 7 on Tuesday. And what I'll do is save the rest of the time if you need to ask questions about the other chapters, maybe some more examples. And then if not, have a safe weekend. We'll see you next Tuesday in chapter 7. Otherwise, this is a good time. We can use the next 15 minutes to go over things if you want. If not,
I only had one more question in terms of like comparing like the ionization energy and the electronegativity. Are the trends the same in terms of like, because I know with the ionization energy, it's supposed to increase up the group from the bottom to the top and then increase from left to right. So is that the same with electronegativity then?
yeah, very similar because if you go from left to right, as you go for electronegativity, the trend is the electronegativity increases. So if I were to compare the electronegativity of, say, let's pull up the periodic table. All right, so let's say you want to compare the electronegativity of, let me mark 2 of them here, of chlorine versus, not chlorine, carbon and nitrogen. Which would you say has a higher electronegativity?
It'd probably be the nitrogen, right?
Exactly, because it's closer to chlorine. Remember, chlorine is your benchmark. That is the most electronegative element there is. So the closer you go to fluorine in position-wise, the higher your electronegativity. Now look
Okay,
at the
so with the ionization energy, it would be higher with that also, right?
exactly. So
Okay.
the same would be true if you look at the IE for nitrogen and carbon. Okay, you'll see that nitrogen has a higher ionization energy simply because it has one more proton and one more electron. So that force to hold on to the electrons is greater, which also tells you that the radius of nitrogen is smaller than a carbon.
Okay, gotcha.
Got it?
All right, perfect.
All
I
right.
think the only thing I still need to practice is my what is it? The electron configurations, because
The electron configuration. Yeah.
I keep on messing up the very end of it. So that's
Okay.
that's
Well,
all I
just
can work on.
yeah, just remember what period you're in. Like, you want to do one real quick? Here, let me.
Sure.
Okay.
I mean, once you throw in the D's, I get really messed up. But
Uh-huh.
yeah.
All right. Well, why don't you do phosphorus?
Okay, so phosphorus. So
Where
that's on
would you
like,
start?
let's see, it's going to be in the third period,
Okay.
and it's going to be in the P sublevel. And so basically that will end with 3P3, correct?
Okay. You're
They'll start with
missing.
1S2.
You're miss. Yeah, but you're in the third level, which you're correct. So remember, let me get the arrow. Let me get a different one. You're going to fill your electrons from here to here, correct?
Right.
And then from here to here,
Okay.
and then from here to here. So when you said 3P3, you were correct, but what were you missing?
All of the other stuff.
Well, in the third level, what will be in the third level? What do you always fill first?
It would be 3S2.
You
and
got
then
it.
3.
And then
I think
3P.
one of my problems is that like I'm looking for the period that it's in, and then I'll look for it like its sublevel that it's in. And for some reason, I just want to solve that end one, and then I just fill in all the rest as full. And I think that's
Okay.
where I keep on messing it up, especially when you threw one in that had a D in it. That's
Yeah.
kind of where it threw me for a loop.
Okay.
It's 'cause, like,
Well,
they're
don't focus on the D's right now. Just try the first 20. Okay. I mean, start with hydrogen.
Okay.
Okay. Start with hydrogen and let me clear this up. Okay. Just start with hydrogen. What would that be?
That would be 1S1,
Okay. Helium.
and that'd be 1S2,
Okay. Lithium.
and then that would be 1S1, 2S1, or right? No. I don't know. That'd be 1S1, then 1S2, and then 2S1,
You got it. Okay. Now beryllium.
and that would be. Do you just want me to like recite the whole thing, or do you just want me to recite part of it?
Just give me the valence.
Oh, just the valence?
Yeah.
Then that would be 2S2?
Yep. And what about boron? We'll stop at neon.
Okay, and then so boron would be 2, it would be 2S2 and
the valence.
2P1, right?
You got it. You got it. And carbon?
2S2, 2P2.
You got it. And if you went all the way across neon, what would that be then? Just the valence.
Just the valence would be 2S2 and 2P6.
You got it. And then if you needed to write the whole thing, you actually include the 1s2
Yeah.
and then what you just told me.
Yeah.
And then if you wrapped around to sodium, now you're dealing with the third period, and you do the same thing which you just did. Okay.
Yeah, then it would be 3S1, and then so on and so forth.
And so on and so forth. Okay. Now the thing that you probably messed you up is when you get to 21.
Yeah.
Okay? So give me the valence for calcium.
So the valence would be it would be 4s2.
You got it. Okay. And so and then plus all the other stuff behind it, right? If you needed to
Yeah.
write the whole thing. Okay.
Uh-huh.
So now you hit 21. Okay. 21 is part of the D block. That's where
Yeah.
that's where they come in. The thing to remember when you hit the D, you just subtract 1 from the period it's in.
Okay. And so instead of, say, with calcium, which would be 4s2, then with Se would be it would be 4s2 and then D or 3d1.
You got it. And if you went all the way across the zinc, where would that be then?
Zinc. Eep, I really don't know.
What? No. You okay? Continue. Okay. Maybe I jumped ahead. You got 21 correct. Okay.
Because with D, there's 14 total that
No,
can go in, right?
No. How many columns do you see from my 2 arrows?
Oh, 10. There's 10 there.
Yeah. So if I said, okay, what would be 22? What would you have done?
It would have changed to 3d2, right?
You got it. Now shoot across the zinc.
That'd be 3d10.
You got it. Okay. And so the valence for zinc will be 4s2, 3d10. Right?
Okay, so when you're writing that out, like especially when you hit GA, so
Yes.
it would be 3d10 and then you would write in 4. That's okay. That's the one that threw me off is when you get to the 31.
Well, you're back. Yeah, you're back to the P's. Remember, the P's are in the 4p1. Right? Remember how many columns are there in the P block?
There's 6 there.
Exactly. So starting with group 3, there'll be P1, P2, P3 across the board, all the way to P6 when you're at the noble gases, correct? And so when you did 31, okay, just like you did, I'm going to do let's say number 31, so that'll be GA.
Yeah.
Okay, and I'm going to do the shorthand.
Okay, it was the longhand that confused me at that point because like once you introduce the D's, I even tried looking up YouTube videos on this, and with some of these ones that introduce the D level and then increase from there, they had it written out to where it was like S then P and then D and then P again.
Yes, and that's what I'm going to demonstrate here.
Okay.
So you agree that let's start with, we were at potassium, and I'm just going to do the valence because you understand you got everything up to number 18 with no problem, correct?
Yeah.
Okay, so I'm going to start with potassium. And so potassium, we said it was 4s1.
or 4s1.
Okay.
4s2 for calcium.
And then we did that for calcium, okay?
Yeah.
And so then we went to 21, okay? And so what I'm going to do is I'm going to put in brackets argon because that tells you that's everything behind potassium, okay?
Okay.
Okay. And so now at this point, you are at calcium. And then I say, well, go to 21. Okay, 21 is the D block. It belongs in the D blocks. And that's where the D comes in. And the thing to remember is note the period it's in and subtract 1. So that becomes 3D1. And that's what you stated, which is correct. As you shot across, and if I went to 22, then guess what? That's 22, correct?
Yeah.
Okay, and if I went all the way to zinc, then that would be 10. Okay, at this point, I go to 31. Well, now I'm back in the P block. All right, so
Yeah.
I go back to the 4 period, and then I start introducing my P, which is that 4P1.
Okay.
Now, what some people do technically, because 3 is much less than 4, they will put
put that
3D. Exactly,
Put
they'll
that
put it
3D
right before the
before.
4. Yeah, I would accept it like that. I don't have a problem with that, the way it's written there.
Okay.
And then, so now we're at 21, and if I shot across to number 31, if I went to 32, guess what? Wouldn't that be simply 2?
4P2.
And if it went all the way across to Krypton, 36, wouldn't that just be that?
Yeah.
Okay. Now, I'm going to go around the horn and go to 37. Guess what happens? Where did I start? I'm going to 37.
You're going to start in the 5th period.
5th period. Okay, where's 37 at? It's in the S block. And back to the S. Okay, and it's in group 1, right? So I
Yeah.
only have 1 valence electron. Okay.
All right. So when it comes to the D block, when those Roman numerals, you were saying that the Roman numerals kind of indicate like how many valence electrons there are.
Yes, for the main transition on the 1A all the way to 8A.
Okay, so yeah, when you introduce the D block into like any of these equations, then like that's those, for some reason, those Roman numerals like are throwing me off when I'm trying
Yeah,
to.
but ignore the Roman numerals when you get to the D block.
Okay,
Okay.
all right, so yeah, just completely, all right, got it.
Yeah, just ignore them. Okay, so we are at 5S1, and if we went to strontium, number 38, that would be 2, correct?
Wait, which one were you talking about?
38.
Okay, yeah, that would be
Okay.
2.
Okay. Now, what if I went to 39? What would you do?
Introduce 4D.
You
1?
got it. 4D1.
Okay, so it's a lot easier to just look at the table and kind of just move across rather than just looking at the end of it to see what it's going to be.
Exactly. I mean, that's why I prefer the periodic table, because just keeping, remembering the S block, the P block, the D block, and the F block. And then remembering that when you get to the D block, you subtract 1 from the period. Now, the F block, if you ever get to that, instead of subtracting 1, you subtract 2 from the period. And so when you get to number 59, that would be 4F. Okay. But we're probably not going to get to the 4F.
All right, good, because yeah. I don't think my brain can handle that right now.
But you went all the way. You did all the way 39, and if we would have continued from 39, what would be number 49?
Then 49 would go into 5P1, correct?
No, 49.
Yes.
Oh, I'm sorry, 48. Sorry.
Oh, then that would be 4D10.
You got it.
Okay.
Now, yes. Now, if you went into 49.
Yeah, which would be 5P1.
Okay. 5P and 1. And then if you went to 50, which is what people brush their teeth with, that's stannous.
That'd be 5P2.
You got it. Okay, and you show all the way across the Xeon. That would be 6.
Yeah, that'd be 5P6.
Yeah, and that's, you see how it goes sequentially? And
Yeah.
just using the periodic table?
Yep.
Okay.
I was just looking at how some people were writing out like I was trying to watch some videos to try to better understand it, and I was watching some people like how they would write out the electron notation differently, like placing the D level, like they were trying to put it like in numerical order in their electron notation, which is what really threw me off.
Okay. And so, yeah, normally, like I said, like the first part, 4s2, 3d10,
Uh-huh.
technically you should put, once you're done with the 10, you put it in front of the 4s because it is in the, you know, it's a smaller number. It's in the third period.
Okay, but you'll accept it as is.
Oh, yeah, just like that. If this was general chemistry 1, you would have to write it in the correct sequential format. But
Okay, so the only time you'd have to put that 3 in front of the 4s is when you filled up the Ds?
yeah.
Okay.
Well, some let me restate that because some professors prefer that you put it even if you're a D1,
Okay.
which is technically is correct. But that can be confusing sometimes.
Yeah,
students.
that's what was really
Okay.
confusing. How it
And
was.
so if you follow this format, which I would accept like this is just following the periodic table.
Okay, so if
Okay.
there's any Canvas test that covers this up to the D block,
Uh-huh.
then you'll make sure that Canvas will accept that as a correct
Yeah.
notation. Okay,
Yeah.
perfect.
And if Canvas doesn't recognize it for, maybe add an extra space or something, and definitely I state over and over again, just send me an email. I'll be more than happy to go in there and look at it. 9 times out of 10, it's correct and you got your points.
All right, perfect. Well, that's all the questions I have.
Okay,
All right, thank
all
you.
right. You're welcome. Anybody else have any questions?
I think I'm good. Thank you.
All right, well, thank you. And now I'm going to go ahead and shut it down. I'll see you guys next week.
Thank you, sir.
Thank
All
you.
right.
Bye.
Okay. Well, Amanda, you're saying about soap?
Oh, yeah, I don't use oil cleansers on my face. I just use
Oh,
soap.
okay. Yeah, then your makeup must be very potent to be removed.
Not really. I just don't like using oil cleansers because they make my
Oh.
face super oily.
Oh, okay. All
I
right,
just-
well. Okay, well, a lot of soaps have some oil in there. If it's coming off, then it's got to be what kind of soap is it, just out of curiosity? Is it hand soap?
Yeah, I just use hand soap. I don't bother spending a bunch of money on face soaps.
Okay, well, that's good. I mean, yeah, you don't have to spend any money. That's a
Yeah,
good thing.
it probably explains all the wrinkles on my face too, but that's okay. I'll
Hey,
live with it.
that's, hey, we all got them. It's called. All right. Okay, then
All
we'll.
right,
All right, you too. Bye-bye. Bye, guys.